Today, we're going on a quest. It's a journey that starts with something you can do with your hands and ends right at the edge of what's even possible for computers to solve.
So let me just ask you this. What in the world does sorting a deck of playing cards have to do with the massive, globe-spanning network that runs the entire internet? It sounds like a random question, I know. But believe it or not, the answer to both is built on the exact same idea.
And here's the thing, you are actually already an expert at solving one of the most classic problems in computer science. You just do it without even thinking about it. It's pure instinct.
Okay, picture this. Someone deals you a messy hand of cards. What do? Well, chances are you do something like this. You keep a little sorted pile in your hand, and as you pick up each new card, you just find its correct spot and slide it right in. Simple. The cards you're holding are always in order. It's just a totally natural human thing to do.
But see, that's the catch. A computer doesn't have instinct or intuition. To get a machine to do what we just did, you have to spell it out. I mean, you have to break down every single action into a set of perfectly clear instructions. You have to give it a recipe.
And that recipe, that's what an algorithm is. It's a finite, step-by-step guide that if you follow it exactly, will get you the right result every single time. It doesn't matter if you're sorting cards or baking a cake, the recipe is key.
And of course, every recipe needs a kitchen, right? In computer science, our kitchen is what we call a model of computation. For our purposes, we're going to use a really simple model where the computer does one thing at a time, no multitasking. And that's super important because it lets us count every single step an algorithm takes. It keeps the playing field even.
So let's write our first recipe. We're just going to take that intuitive way we sort cards and translate it step by step for the computer. This is going to be our first kind of clumsy brute force attempt.
We call this algorithm insertion sort, and it works exactly like it sounds. You grab the second card, you compare it to the first, you put it in place. Then you grab the third card, compare it to the two you're already holding, and slide it in. You just keep doing that over and over again until you're through the whole deck. Easy enough, right?
And you know what? For a small hand of cards, it works perfectly. It gets the job done. But our quest can't stop there. What happens when we change the scale of the problem? I mean, what if you're not sorting 5 cards, but 5 million pieces of data? All of a sudden, our nice, simple recipe, it might not be nearly good enough.
To understand why, we need a way to measure how efficient our algorithm is, and we call this time complexity. Now, forget about seconds or minutes. What we really care about is how the number of steps an algorithm takes grows as the amount of stuff you feed it, we'll call that n, gets bigger and bigger. It's all about that growth curve.
For our insertion sort, that growth curve is, well, it's ugly. In the worst case, we describe its complexity as O of n squared, or big O of n squared. What that means is that the number of steps it takes grows quadratically. So if you double the number of items, you basically quadruple the amount of work. And just look at how quickly this gets completely out of hand. Sorting 100 items takes about 10,000 steps. No big deal. But 10,000 items? That's 100 million steps. This isn't just a little bit slow, this is a total disaster. Our simple algorithm has hit a brick wall that it can never, ever get over.
So our quest needs a new plan, a smarter strategy, one that can handle huge amounts of data without just completely falling apart. We need to work smarter, not harder.
And this brings us to one of the most elegant and powerful ideas in all of computer science: divide and conquer. The concept is so simple, it's beautiful. Instead of wrestling with one giant, scary problem, you just 1. Break it into smaller, bite-sized problems. 2. Solve those little problems. And 3. Stitch all the little solutions back together. It's how you make an impossible task possible.
So let's see how this new strategy does against our old one. We're going to have a showdown. In this corner, our brute force insertion sort, and in the other, a champion of divide and conquer, an algorithm called quicksort.
And here is the absolute game-changing difference. Insertion sort just plods along one item at a time. That's what gives it that brutal O of n squared complexity. But quicksort is clever. It uses divide and conquer to keep chopping the problem in half. That halving action is the magic secret behind the log n part of its complexity. It means you're not comparing everything to everything else. And the impact of this one little change is, well, it's staggering. Look at these numbers. They speak for themselves. With 1 million items, quicksort takes about 20 million steps. Yeah, that's a lot, but it's totally manageable for a modern computer. Now look at our old friend insertion sort. It would take 1 trillion steps. That's not just slower. That's the difference between your program finishing in a few seconds or in a few decades. This is why finding the right algorithm changes everything.
And this brings us to the final leg of our quest. Because this journey from a simple, slow algorithm to a mind-blowingly faster one, that's not just a story about sorting things. In a way, it's the story of computer science itself. This constant hunt for better, smarter, more efficient algorithms is what drives almost all progress in technology. These same principles of analyzing complexity, of divide and conquer, they're fundamental to building everything from the stunning graphics in a video game to the complex logic inside an AI. But what if for some problems there is no champion algorithm? What if some problems are just fundamentally hard? As some of the pioneers in this field pointed out decades ago, there's a whole class of problems where we have very good reason to believe an efficient solution might not even exist. These are the monsters at the edge of the map. They're called NP-complete problems. Think of things like the famous traveling salesman problem, finding the absolute shortest route to visit a bunch of cities, or incredibly complex logistics problems. For any of these, we have yet to find an efficient algorithm. And here's the wild part. They're all connected. If you could find a fast solution for one of them, you would have a fast solution for all of them. It is one of the biggest, most profound unsolved mysteries in all of science. And that's where our quest leaves us. We've journeyed from a simple hand of cards to a deep fundamental question about the absolute limits of what we can compute. We found brilliant ways to solve many problems, but maybe the most exciting frontier is understanding the problems that we can't. If some challenges are truly mathematically hard, what does that mean for the future we can build? And what puzzles are simply destined to remain forever unsolved?